Hey guys, here's a quick video on how to use the right-hand rule. It's a little bit tricky because there's actually two right-hand rules. There's the simple one, which I'll talk about first, that most people learn when they're beginning to learn about electromagnetism. And then there's the full right-hand rule, which is the one you'll usually hear being described on the internet in physics problems for more complicated applications and more useful applications too. So first, what is the simple right-hand rule? Well, it's being described in this diagram. You simply take your right hand and you imagine wrapping it around an imaginary wire. And if that wire is carrying a current through it, if particles are flowing and those particles have a charge, then there's electric current, and that will generate magnetic fields around the wire. But what direction? Are they swirling clockwise or counterclockwise? Well, here's the rule. You grasp a current-carrying wire with your thumb pointed in the direction of current flow. In this diagram, the current is flowing up, so we point our thumbs up. And then the only other thing to consider is, what are your other fingers doing? So right now, my other fingers are swirling from the top, what looks like kind of a counterclockwise direction. And that would actually be the direction that the magnetic field flows. So it's kind of weird because we expect when in physics something moves up that its effects move up, but that isn't the case when it comes to electromagnetism. There's all kinds of different dimensions thrown into it. So this is the simple right-hand rule because there's only two things to consider. There's the linear motion or velocity of the charged particles, and then there's the rotational dimension of the magnetic field swirling around. So it's complicated, but it's not quite as complicated as the three-dimensional full right-hand rule. So that's the more useful one, so I'll spend some time building up to that. So here's something that you need to consider anytime you're dealing with vectors in three dimensions. And again, a vector is something that has magnitude, so an amount, and direction. So left, right, up, down, north, south, east, west, what have you. So electric fields and magnetic fields and forces and accelerations, all of those things are vectors. And when we're dealing with three-dimensional physics problems, or math or anything that uses vectors, you have to start finding ways to talk in three dimensions, even though to a reader or to a writer, you might only have two dimensions to work with. So the most common way of representing a three-dimensional vector, in our case, it's going to be our way of representing fields, is to think about an arrow. When you shoot an arrow, there's a point on the end that's supposed to impact the target, and that's the front of the vector. That's where the vector is heading towards. And because the front of the arrow is a point, we use this kind of symbolism here to represent the vector pointing out of the page towards you. So this is kind of represented by this diagram here. The person's eye observing the arrow, they see the tip of the arrow, so we show that as a dot heading towards them. The back of an arrow typically is feathered, and those feathers kind of spread out in what could be considered to be a triangular or maybe an X pattern, depending on the arrow and how good at archery you are. And so we represent vectors going away from us into the page as an X symbol. So this is the symbolism you'll see for things going into and out of the page. Dots means out of the page, X means into the page. So remember, it's the front and back of an arrow. So if you got that, then we're ready to start looking at the full right-hand rule. So we're going to need our right hands for this. And there's three dimensions of space that you need to consider. There's the magnetic field that exists in the space around you. There's the charged particle, which is trying to travel somewhere in that magnetic field. And then the third thing is the result of those two things coming together, which is a magnetic force. So here's the right-hand rule. Number one, point your hand, that is your four fingers in your palm, point your entire hand along the direction of the magnetic field lines. So in this case, they're showing the four fingers going to the right, and so you could point your fingers going to the right. By the way, this video might have a little bit of left-right confusion if you're watching me instead of the screen. So feel free to actually do what I'm talking about here with your own right hand, and it'll make a lot more sense than if you're watching me, because there's a little mirroring going on here possibly. So point your hand along the direction of the magnetic field lines. Number two, point your thumb in the direction of the particle's velocity. Now, this is actually so far very similar to the original right-hand rule because your thumb was like where the charged particles were going, and your fingers were representing the magnetic field. So we're still kind of doing the same thing. But now there's a third element. We have our hand nice and flat, ready for this third piece of the puzzle. And here it is. Your palm, the direction your palm is facing, now represents the direction of the magnetic force. There's going to be a force that pushes the particle in some direction and causes it to arc from its path that it's trying to move in. And that's the magnetic force. So there's three dimensions here again. There's the magnetic field, which is pointed in one way. There's the particle trying to move through it, and then there's a third dimension at 90 degrees to both of those where it gets pushed in some direction. So here's another way you can visualize that. When you are looking at a field and a particle is moving through it, it actually matters. It depends what charge the particle is, whether it's positively charged or negatively charged. All of the rules that we discuss when it comes to circuitry and magnetism assume that we're talking about positive charges, protons or positive ions that are moving through a circuit or through a tube or a wire. And so if we suddenly shift our thinking from protons to electrons, all the rules change and the opposite effect will occur. So this rule is based on positive charges. So you need to slap a proton with your palm, as the rule indicates, to high five it for being so positive, and you should backhand an electron, whack, for being so negative. Tisk, tisk, electron. So we use our palm, as the rule implies, for anything that's positive, because that's by default the types of charges we'll be talking about in our problems. But if there's an electron at play, you need to consider using the back of your hand instead of the front of your hand to think about where the forces will go. Here's a visualization of this. Down here we have a magnetic field with X's. Remember what X's means. It means that the field is pointed into the page, away from you. And you can take your right hand and see what would happen to the proton and electron, which are colored red and blue in this example. So first we take our fingers, we point them into the screen or into the page, because that's where the field is pointing. That's number one. If you look up at rule number 2, it says point your thumb in the direction of the particle's velocity. Well, both of these particles are going up, and I'm just starting with the positively charged proton. So I'm pointing my thumb up. And then once I point it up, I look at number 3. It says your palm now points in the direction of the force. The force. Ugh. So the electromagnetic force is going to be coming out of my palm here, so it gets pushed in that direction. And so you can see the proton arc in the direction that your palm is now facing, with your right hand, of course. You use your left hand and everything is backwards. So now looking at that negatively charged electron. Once again, point your fingers towards the screen or into the page, as they say. You point your thumb in the direction of current flow. That electron is trying to go up, so that's where it's headed. And usually this is where we'd say, oh, our palm points in the direction of the magnetic force. But in reality, this is an electron. It's negatively charged, not positively charged. So the rules flip. So now it's the back of your hand that tells you what direction the force will push this particle. So you backhand the electron for being such a negative Nancy. You say, snap out of it, electron. And then if there's a proton, you say, wow, you're really positive, high five. And you use your palm to figure out where it'll go. So there's a little look into the right-hand rule. So now let's practice with it. Here's 2 magnetic fields, and I've just plopped 6 particles onto that field. And it says, predict the direction of the magnetic force on each particle. So let's look at the top left particle first, the red proton in the field labeled B1. B, of course, stands for magnetic field. So this magnetic field is pointed into the page. So we point our fingers into the page. Then we look at what direction the particle is moving. Again, don't pay attention to me. Pay attention to your own right hand and your own screen, because I might be flipped. But the particle is going in a certain direction. And now if you look at your palm, the palm points up. And so the particle should receive an upward magnetic force. Again, this is a positively charged proton, so your palm is what you use. Now I'm going to look a little bit lower at that blue electron in the same field. That electron, well, let's see, it's in a field pointed into the page. So there's where all my fingers go. My hand is going to point my thumb downwards because that's where the traveling particle is trying to go. And it's an electron. It's negatively charged. So I'm going to use my backhand, whack, to tell that electron where to go. So it should go to the left. Now, the last one in this field is a proton, and it's headed upwards. Okay, let's still the same magnetic field. So let's point our fingers into the page. And now let's have our proton facing upwards because that's the direction it's traveling in. And then lastly, our palm represents where positively charged particles will go. So whack, it should go to the left. So you can see there were 3 different results here because we had different types of charge traveling in different directions. But the thing that was the same here was they were all in a field that was pointed inward. So it was easy to kind of go from one to the other. Now we're going to flip it. Now in field labeled B2, we have a magnetic field that is pointed out of the page towards us, towards our eyeballs. Again, that dot is like the arrowhead coming at you, the tip of the arrow. So I'm going to start with the electron on top of field B2. First, I point my fingers towards myself because that's where the field is going. Then the particle is traveling in a direction that I'm now representing with my thumb. and then it's a negatively charged electron, so I should backhand it. Whack, quit being so negative. So that should be an upward force. Now the proton, well, it's in a field that's pointed out of the page, and it's headed downward. This is kind of awkward. You're going to have to move your arm at some point when you're doing a whole bunch of these. And it's a positively charged particle, so based on where my hand is located right now, this should be a slap across the face for me because I used my palm. There we go. That worked out pretty well for you guys, not for me. And the last one, there's a negatively charged electron. It's in a field that is, again, pointed out of the page. It's traveling in this direction, and it's negatively charged, so we backhand it. That was a fun one. And so now it goes down. So there's 6 examples of using the full right-hand rule. It's actually kind of fun when you get the hang of it. So that's the right-hand rule. And we were just doing examples. Let me go back for a second, sorry. We were just doing examples where there's already a magnetic field just there when the particles arrive. But remember that those particles, as they're traveling, that's current flow when particles that have charge travel. So those particles themselves, especially several particles, if they were all in a wire together, could create their own magnetic field. And so now we're going to get into how do we use these two right-hand rules together in some more complicated conceptual scenarios. So get myself out of the way here. On the left, you can see that old diagram. This was the simple right-hand rule where you just grab a wire and your thumb points in the direction of current flow and your fingers make the magnetic field. Because that still applies, that's still a real thing. Just because it's the simpler version doesn't mean it's less real. If we look at the diagram on the right, there's a wire with that purple arrow showing that there's current flow right around here. And that current flow is going up. So if we grab that wire, it's basically the same thing as what was in the diagram on the left. We have this swirling red magnetic field. And if there's a particle, like right here labeled Q naught, that particle right there, if it's traveling upward, it's going to be exposed to the magnetic field created by the wire. And therefore, it's going to be a traveling particle in a magnetic field. So there's going to be a force in that third direction. So now we're combining the two. So now we're going to get into an actual sort of conceptual problem here, because current carrying wires can actually exert forces on each other. And even particles that are passing by each other exert magnetic forces on each other. So we're just going to simplify it and stick to wires, because wires are a more tangible object to us in our minds. So on the left and on the right, there's the exact same scenario, the same setup, with two wires carrying current. But one diagram, A, has the current going in opposite directions, and B has them going in the same direction. And it's labeled as repulsion and attraction. And again, the title up above says current carrying wires can exert forces on one another. And it's true. If you hook up enough voltage to two wires that are carrying the same current flow, you can actually make the wires stick together almost magically, or you can have them repel away from each other. So why does this happen? Well, we're going to look at examples A and B and try to figure that out. So on the left, I'm looking at the repulsion example, and I can see that there's a little red arrow labeled B here. So that's the magnetic field that is that wire 2 is exposed to. Well, where did that magnetic field come from? Well, it probably came from wire 1, because we know that wires can create magnetic fields. So let's just start with wire 1. Let's see where the field came from, and then we'll go from there. So I'm seeing wire 1. I can see this purple arrow pointing current flow out of the page. So I'm going to point my thumb out of the page and use the simple right-hand rule, because this is a wire, so I can just grab it. This is going to be the simple right-hand rule. And if my thumb is pointed out of the page, I can see that my fingers are wrapping around in this direction. So if I keep coiling my fingers around, and I really think about this three-dimensionally, I can see that there should be a swirling magnetic field. And I'm going to use the color red here. There should be a field that kind of goes under it and around it like this. So that's the field that this wire should create. And if I consider that fields pretty much go out for infinite distance, they just get weaker and weaker and weaker, I can kind of extend that and say, well, hang on, this field probably also goes out a little bit farther, maybe something like that. It would just be weaker out here. I can't really draw that well, but it's eventually going to reach a distance kind of like this. Never mind my terrible artwork. And so it's eventually going to reach this wire over here. It's going to be weak, but it is going to reach there because fields go out for infinite distance. So now I'm looking at wire number 2, and I'm seeing that it has charged particles that are flowing in some direction. It looks kind of like three-dimensional, like it's going into the page. And that charge that's going into the page is exposed to a magnetic field. So what's going to happen to it? It's going to have a force put onto it. So I'm going to use the full right-hand rule now, because now we have kind of 3 dimensions of things happening here. So I got to figure out what this force is going to look like. So I'm going to take my hand with my 4 fingers, and I'm going to point it upward, because at that exact spot, right around here, that is the location where the field is pointed upward. So upward go my fingers. And then I'm going to point my thumb in the direction of current flow, which is a little bit awkward for me here, but that's into the page. So now that I've got these 2 situated, where's the force? Well, I'm assuming conventional current, which means positively charged particles are the ones that are flowing. And so that means my palm is going to be what I use. So I high five the positive particles. So now you can see why there would be a force that pushes outward. And if you were to do the opposite of what I just did and look at wire 2 first and think about the field that it creates, that it exposes wire 1 to, you would have actually gotten the exact same result. You would have gotten that the force pushes it away. So either direction you start that problem from, you can figure out that those 2 wires will repel. And you have to kind of start with the simple right-hand rule and then build up on the other wire to the more complicated full right-hand rule. So it's a little complicated. Would you believe it? It's physics. So real quick, I now want to do the attraction one, and this can now go a little bit faster. So the attraction example, over here we can see that there's a wire with a current labeled I1, and I'm going to just grab that using the simple right-hand rule. So current's going out of the page, so I grab it, and I can see that once again, like before, there's a swirling magnetic field. So that would look something like this. I'm going to try my best to draw it 3-dimensionally, just like before, and I'm just going to skip right ahead to that really big circle where we can see right there that the swirling field created by wire number 1 is going to be received and felt by wire number 2. So I may have covered it up a little bit. Let me see if I can erase this just to make sure you guys can see that right there. But there is a current traveling out of the page in wire 2. So I'm going to use the more complicated right-hand rule now, the full right-hand rule. So your fingers go in the direction of the magnetic field, which at that point right there in space is upward. So there go my fingers upward. The thumb goes in the direction of current flow. So that's out of the page towards you. And these are, again, we're assuming positively charged particles flowing. So we use our palm to show us where the force is going to go. There you go. So that vector for force actually pushes the wire towards the wire that was affecting it. And just like before, if you were to reverse it and start this problem by looking at wire 2 instead of wire 1, you would get the same result. So these 2 wires are both mutually attracted to one another, just like the 2 wires in the reversed example were mutually repelled by one another. So that was pretty complicated, but if you really think about this and you know both right-hand rules just totally off the top of your head and you know them backwards and forwards, you can solve a lot of conceptual EM problems just by moving your hand around in funky ways. And this year you can do it from the privacy of your own home in 2020, so you're not going to look like a fool like most people do every year. So that is, and by the way, if you look like a fool moving your right hand around during the AP Physics 2 exam, that's how you know you're doing something right. People who aren't moving their right hands around, they're the ones who don't know what they're doing. So that's going to take us, I think, to the final little problem here. And let me clear the screen. Okay, so here's the final slide for this presentation. It says, is the coil with current I2 attracted to or repelled by the wire with current I1? So let's look at this diagram and break it down a little bit. We've got a wire that has current flowing towards the right. That current flow is labeled I1. And then we have this coil that's being split up into 2 little segments here, but it physically is all connected. It's just a coil with current moving around and around and around. Now I could ask the question, where does this current come from? Where's the voltage source? How much resistance does this have? But the nerd in me needs to just quiet down for this simple conceptual problem. So the current in the wire is flowing. That's going to create a magnetic field everywhere on this page. And I'm going to start by taking my right hand and using the simple right-hand rule. So I'm grabbing the wire with my right hand and I'm making sure my thumb is pointed in the direction of current flow. From that, I can see that there's a pattern where my fingers are swirling around in a certain direction. Here's where things get a little bit tough, and I need to draw 3-dimensionally what this field looks like. So I'm going to grab my pencil one more time. And again, 3-dimensionally means you have to use crosses to show something's going into the page or dots to show that something's coming out of the page. So where would there be dots? Well, I think that's going to be on top based on how my hand is moving. So all the dots will be up here. These will be the spots where the field is coming at us out of the page. And down below is where it will go back into the page. This is the only real way to represent this accurately. I'm going to help you guys out a little bit maybe. I'm going to draw a little swirlies here. This is the swirling magnetic field. Feel free to fast forward like 15 seconds to see me draw this. Ooh, that was a bad one. There we go. And we'll try to get this three-dimensionally here going behind the wire. Man, I should have been an art teacher. Ooh, I missed my arrow. That's okay. We don't need arrows on all of them. Ooh, now the folks who love consistency are upset. Sorry. Okay, so that was your freebie. That's the only 3D you're going to get. But if you wrap your right hand around this wire, you should see that this is the way the field is working. So now without the swirlies, this field goes out to infinity, into infinite distance. It just gets weaker and weaker and weaker the farther away you are. So I'm going to keep putting X's right here. Voila, the magic of technology. That would be really boring to have watched in class. So here's my magnetic field. Now, the one thing I didn't really take a ton of care to draw is the fact that the field is stronger near that wire than it is down below, because as you spread out far away from the source of any kind of wave or field, it gets exponentially weaker as you go farther away. So now we can actually get to answering this question. Is the coil with current I2, so that's this coil down here with the clockwise direction of current flow, is it attracted to this wire or is it repelled by this wire? This is more complicated than the previous question because now there's two directions and it seems like maybe one of them would be attracted while the other one's repelled. So let's just start by analyzing the top segment and then we'll look at the bottom segment. So we have in this little top section right here, maybe I'll highlight this using blue or something like that. In this section of the wire, we have current flow that's headed in one direction and a magnetic field that's headed in a different direction. So I'm going to use the three-dimensional full right-hand rule for this. So I'm going to point my fingers into the page. I'm going to point my thumb in the direction of positive current flow. And again, I'm assuming positive charges, so I'm going to use my palm for this. So there's a force that pushes the top of the wire upward. So there's my force vector. So the force, there we go, that looks really weird. Looks weird covered up. Let's try that F one more time. It's really hard to get an F in physics. That's what I tell all my students. Okay, so there's the force vector. It's clearly attracted to the wire. Now let's look at the bottom segment. So looking at this segment, right here. I'm going to do the same thing I did before, use the full right-hand rule. My fingers are going to point into the page because that's what the magnetic field is doing. My thumb's going to point in the direction of current flow. And again, I'm assuming it's positively charged current flowing. So I use my palm. So it's going to push away. It's actually going to be repelled away from the wire. There's my force vector right there. So now the question is, what the heck is this thing going to do? Is the coil going to rip itself in half? Well, no, we're assuming that it's nicely all attached and nothing is going to explode. So we now have to ask ourselves, is one of these forces going to be stronger than the other one? And you might have figured this out by now because of what I mentioned. I just didn't draw it. But the force here is actually going to be stronger. This is going to be a larger force in the top section than it is on the bottom section. Why is that? It's because, as I mentioned, there's actually a stronger magnetic field in this location than there is in this location. Why? Because the distance is greater. So if I were to measure out this distance here, call it D1, and measure out this distance, call this D2, those distances would be plugged into formulas that tell you how strong the magnetic field is. And plugging in a smaller distance would actually result in a greater strength of a field. A stronger field means stronger forces. So that was a pretty complicated conceptual example. It may be useful to you on the AP exam or just in your standard physics class. Hope that was useful. See you in the next video.